Well, hello again. We are continuing on. There's so much to learn. We could do this for years if we really wanted to. All right. We're taking a look at something that's a little bit different. I find a lot of first time users on this concept of resonance have a little trouble with it because it's kind of like, eh. Remember, the Lewis theory isn't perfect. It's a great basic theory. There you go. It's a great basic theory. But it doesn't work for everything. So we're going to take a look at one of these situations where we're like, a situation where, hey, maybe we get some molecule or some kind of species and we have to draw a Lewis structure. But it turns out there's several, like 2, 3, or 4 sometimes that actually work. Right, so maybe I got to place some multiple bonds somewhere, and I go, well, it could go there, or it could go there, or it could go there. I could put a triple bond here, or 2 double bonds there, right? What if you got a 6n plus 2 minus number of valence electrons of plus 6, right? That could be 3 double bonds, a triple bond and a single bond, a triple bond and a double bond. So there may be several options, and they're all valid. So remember, a Lewis structure, just because it's valid doesn't mean it's necessarily correct, right? We can say, hey, if this Lewis structure doesn't work, we can say it's not valid and not correct. But if it's valid and everything works out, we think it's correct, but it's not necessarily. So there's more advanced theories and models that we'll look at later. This is one of those ones we're going to have to kind of, not really fudge it, but, you'll see what we do. So when we run into that situation where we've got 2 or more Lewis structures with the same atomic connections, right? All the atoms are in the same place. They have the same skeletal structure that way with everything with single bonds. And then we add double bonds, triple bonds, lone pairs, all that kind of stuff. And there's 2 or more options, and they're all valid. All the octet rules and duet rules are satisfied. Use the proper number of valence electrons. If we get 2 or more possibilities, those are called resonance structures, and they usually just differ by the placement of the electrons. Oh, so how do we represent that? What's really going on? Let's do an example just to show you how it looks, and then we'll talk about what it means. Let's try this one out for size. There's a lot of polyatomic ions we'll see show what are called resonance. And like I said, how we look at it once we get this problem finished, there's kind of an easy way, and then there's a more specific way. I might mention the more specific way. I don't know. We'll see how I feel. So let's do the Lewis structure for the carbonate ion, CO3 2-. So please pause this and do the number of valence electrons, step 1, 6n plus 2 minus number of valence electrons, step 2, step 3, central atom, step 4, skeletal structure, place in the multiple bonds, step 5, add all the lone pairs and check it. Do all that for me real quick, all right? And I'll walk through it here. So we got 1 carbon, correct? That is in group 4A. So 1 carbon throws 4 electrons into the pot. We should know that by now, right? Look on your periodic table. It goes 4A. If you remember, so you just count across 1, 2, 3, 4A. Boom, right there. Oxygen. 1, 2, 3, 4, 5, 6A. So we got 3 oxygens. So let's do the oxygen. Each throwing 6 into the pot. Right, so we've got 18, 22 so far, but look at the negative charge. We've got to subtract that. So subtract that -2 charge there. So we have to add 2 more. That -2 is because we added 2 more electrons to get all the octet rules satisfied. So 18, 19, 20 looks like 24. And that's an even number, so it's not going to be a free radical, right? If that was odd, that'd be a free radical. Let's do the 6n plus 2 minus number of valence electrons. In this case, there's no hydrogen, so we count all 4 atoms. So n is equal to 4. So let's do this. So that's going to be 6 times 4 plus 2 minus 24. So that's 24, 25, 26 minus 24. That, my friends, is plus 2. Now, look for electron deficient species. No boron, no beryllium, no aluminum, right? And it's not an odd number, so we don't have an electron deficient structure. There's only 1 carbon, so we can't have a carbon ring, so that must be a multiple bond. It has to be. So 1 multiple bond. So that obviously that must be a double bond. So we got to cram that double bond in there somewhere. Bond, double bond. So let's do, now carbon obviously is way less electronegative. Look for symmetry. Oxygens don't like to bond to each other because they're highly electronegative. So we're probably going to have all three oxygens bonding to that carbon in the center. So let's do that. Let's put the carbon here. With the three oxygens. Start with single bonds. Now we need to put a double bond in there. You see the problem? Should we put the double bond there? Should we put it there? Or should we put it there? They're all equivalent, right? Where does it go? Shaggy. Alrighty. Since there are three equivalent Lewis structures we could draw, one with a double bond here, one with a double bond there, and one with a double bond there, those are all valid Lewis structures. They have the same atomic connection. They just differ by the placement of that multiple bond. We have to draw all three of them. So we have three valid Lewis structures. They're called resonance structures. Yes, you have to draw all three. No! Call the ambulance! So let's just put the double bond on the left to start. And now let's add our lone pair. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And since it's an anion, we have to put it in brackets. So let's count up 2, 4, 6, 8. Octet rule satisfied. 2, 4, 6, 8. Octet rule satisfied. Carbon's got 4 bonds. Oxygen's got 2. They're happy. 2, 4, 6, 8. 2, 4, 6, 8. Octet rule satisfied. But these oxygens only have 1 bond. Not quite satisfied. Let's count up the total number of electrons. So we've got 8, 16, 24. That was the same one I had trouble with last time, where I could see the 24. You got 8, 8, 8, but I kept counting 26. It just drove me crazy. It was one of those days. So 24 equals 24, so we're good to go. So now let's do, and what we're going to do is we're going to use a double-headed arrow to draw the next Lewis structure, and let's make it up on the top there. So let me erase this for some room. And I'm going to do these a little faster. Let's put the double bond there. Add your lone pairs. And then put your bracket. And unfortunately, there's a third one. And if you want to put the third one down there, kind of make a triangle, that would work as well. And that will have the double bond on the right-hand side. Like so. Complete your octets. This takes a while, doesn't it? So a lot of students dislike resonance structures. You can see why, huh? Because you got to draw them all. And I will put resonance structures. They are all valid, my friends. Now, the problem is, if we went into a laboratory, see this, based on what we see here, we would say, well, one of those bonds would be a double bond, and the other bonds would be single bonds. All right? So we're going to learn later, actually, we're going to do a video on bond length and bond strength and bond order. Turns out that the more electrons you put between two atoms, it draws the nuclei closer together, so it's a shorter bond and it's harder to break. Hopefully that makes sense. So really, that double bond should be shorter than that single bond. And it should be harder to break, should require more energy. So we would expect if we went into a laboratory, we would have 3 different bonds to break, right? Or we could measure bond lengths and go, well, these 2 would be equivalent and longer than that one, which would be shorter. That's what we would expect. That's not what you see. So what you get in lab is all 3 bonds are the equivalent length and strength. They're all the same. And that's not what it looks like here. So this is one of the faults of Lewis theory. It doesn't really work for this very well. So what we do to fix that is say, okay, the actual structure is not one of these. It's actually a blending of all 3. It's not that the electrons here are moving back and forth. They're just spread out. So that extra multiple bond actually gets spread out. And so it's here, a little bit here, a little bit here, and a little bit here. So maybe a third of it's here, a third of it's there, a third of it's there. So really each bond is like 1 1/3 bonds, right? Not quite a single bond, not quite a double bond, somewhere in between, but closer to a single bond, about 1.3. And the true structure is all three of those blended together. Kind of like when you see a hummingbird flying, its wings are here and then its wings are here. But when it's flapping real quick, you don't know where the wings are. They're everywhere at the same time, right? So another thing that people, not really accurate, but people think about the electrons go back and forth so fast it just blurs. Not really what it does. It just, the electrons are just spread out. So we can draw an equivalent structure like that. Most people just leave it like this. I'll mention it and I'm going to do it, but some people will draw, instead of a double bond there, they'll draw a single line with a dotted dash, like a dashed line here to represent a partial. So you kind of see something like this. And that's what they would draw as the Lewis structure of all three combined. But typically at this level, I'm just going to have you draw all possible Lewis structures. Very rarely do you get more than two. You can get three, so this is an unfriendly one. And these are equivalent. So you can think of the fact that all three contribute to the true structure equivalent amount. So the real structure is 1/3 this, 1/3 this, 1/3 this. They're all equivalent. But we're going to run into a situation where we can draw multiple valid Lewis structures, but they're not equivalent anymore. So they may not contribute to the overall structure an equivalent amount. Let's do one of those. So let me make a mention on this because I ran out of board space, and then we'll do one that's a little trickier. All right. So with the carbonate ion, we saw that all the resonance structures were equivalent, which means they all contribute to the true structure in equal percentage, right? And since there was three of them, they all do 1/3 or 33.333 something percent. And if you went in the lab, you'd find the bond lengths and bond strengths are all identical. Hey, hard to show that in a single Lewis structure, right? But a lot of resonance structures you're going to draw, you get these molecules or ions or something, and you can draw these multiple valid Lewis structures, but they're not equivalent. It's not just a simple, it's not symmetric like the carbonate was, and you could put the double bond here, or like ozone, you could put the double bond. You have 3 oxygens, you could put the double bond on either side. Those are equivalent Lewis structures. We're going to run into ones that are not equivalent. Which means they are going to contribute to the overall structure different percentages. We will not be able to, at this level, tell that one will be 25%, that'll be 75%. If there's 3 of them, that'll be 50, 30, and 20. We will not be able to do it to that extent, but we will be able to go, hey, that one contributes more than that one. That they're both valid, but that one's more likely than that one, right? Things, maybe the preferred bonds, preferred number of covalent bonds has been attained more for this one than for that one. So it's technically a better structure, even though they're both valid. See what I'm saying? So we got a way to check that, but not determine the percentages. Let's do one example real quick, and then I'll show you how we can discern which is the better of the valid Lewis structures. Try this one on for size, my friends. Let's do the Lewis structure for cyanic acid, which just says the cyanate ion, OCN minus. And in this case, obviously, the way it's written, it will go, the hydrogen will be attached to the oxygen, then the carbon, and then the nitrogen. Kind of goes in that specific order. So go ahead and do the Lewis structure for me and see if you can come up with any equivalent, I wouldn't say equivalent, valid Lewis structures, right? You will get more than one for this. Although the way I teach you, though, when you place multiple bonds based on giving atoms their preferred number of covalent bonds, you tend to always get the best of valid Lewis structures. So it should seem fairly obvious which one's going to give a larger percentage to the overall structure between resonance structures. But give it a shot for me. Do the number of valence electrons, step 1, then step 2, blah, blah, blah. Pause it and see if you get what I get. Well, let's go. So we got a hydrogen, oxygen. We got 1 of each, so I'm just going to go 1 for the hydrogen, 6 for the oxygen, 4 for the carbon, 5 for the nitrogen, right? Group 1A, group 6A, group 4A, group 5A. So we've got 610, looks like 16 valence electrons. That's an even number, so it's not a free radical. Let's say we don't count the hydrogen, so N is going to be 3 in this case. let's calculate 6n plus 2 minus number of valence electrons. So 6 times 3 plus 2 minus 16. Well, that's 18, 19, 20. So that's the number of electrons we need for all single bonds. But we only have 16 electrons. We don't have enough electrons, so that means we have an electron deficient structure or a carbon ring or multiple bonds. We don't have boron, beryllium, or aluminum, or an odd number of electrons for a free radical, so it's not an electron deficient species. We don't have enough carbons for a ring, so we don't have any organic rings. Therefore, that must be 2 multiple bonds. Covalent bonds. That could be 2 double bonds or 1 triple bond, right? 2 double bonds or 1 triple bond. Let's take a look at the possibilities here. The old shoulders. Well, let's do it in the right order. So we've got H, O, C, N. Start with all single bonds. Let's place our 2 multiple bonds. Let's do it the way we've been taught, trying to give things their preferred number of bonds. So we know hydrogen can only have 1. Oxygen prefers 2, right? Now it already has 2 bonds. So oxygen prefers 2 bonds, right? Nitrogen prefers 3, carbon prefers 4. So if we can't put a double bond there, that would disobey the duet rule. So if we put a double bond there, that would give the oxygen 3 bonds, not super happy. So it really, this carbon has 2 bonds, so it needs 2 more. So you can see the 2 multiple bonds. So we need either a double bond here and here, or a triple bond there. See how that works out? So let's start with what we would think would be best. Would be a triple bond right there. And then we complete the octet for nitrogen, 2, 4, 6, 8, 2, 4, 6, 8. So the carbon has 8 electrons and 4 bonds. Nitrogen has 8 electrons and 3 bonds, which it wants. Oxygen has 8 electrons and 2 bonds, which it wants. Hydrogen has 1 bond. So everything's really happy here. But you see, we could have done the 2 double bonds there, right? And that's not an ion. So let's put the 2 double bonds. So let's do the same thing. But let's put a double bond there and a double bond there. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. This is valid, right? Duet rule. We've got 2, 4, octet rule, octet rule, octet rule. Now the oxygen and the nitrogen don't have their preferred bonds. These are valid, but you can see how this one's probably going to contribute a little bit more. I'm going to show you a specific way to do that numerically, where we could calculate it so you don't have to guess. But these are both valid, but they're not equivalent. All right? Valid, but not equivalent. So valid, but not equivalent. Whoops. Resonance structures. I'm running out of room on my board here. All right, I'm going to get something out of my eye real quick. We'll be right back. There we go. I cleaned it up a little bit there. I was getting squished on the bottom there, so I wanted to start it over again. We don't need everything from the other board. So we have these 2 valid but not equivalent Lewis structures. So let's go through and see if there are any more based on where we can place these 2 multiple bonds. Right now, we all agree we can't put them on hydrogen, but they could go between here and here. This looks like the best one. Now, we could that's the only place to put 2 double bonds, right? We can't put a double bond there, so that's the only option for 2 double bonds. But there's another option for the triple bond. Could we put the triple bond here? Doesn't mean it's likely, but I think we could. Let's take a look. What if we put a triple bond right there? Would that be a valid Lewis structure? Well, let's complete the octets. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. All right. Octet rule, octet rule, octet rule, duet rule. All the rules are satisfied. Now, nitrogen wants 3 bonds. It doesn't have it. Carbon's got, now in every scenario, carbon has 4 bonds. but the oxygen and nitrogen change. So this is also valid. So if you get the 3, now when we did the carbonate, we just did the 3 across. But if you want to do something like this, the true structure is a blending of all 3. So let's write that down. So the actual structure is a blend of all 3. I don't think there's any more we could write out of that. All 3 resonance structures. But this is not like the carbonate scenario where they're all equivalent, right? These are definitely non-equivalent structures. Our guess again would be this one would be have the most contribution because everything has the preferred number of bonds and it's happiest, but not equivalently. Is that a word? It is now. And so this is going to lead us into our next video, which is called formal charges. We're going to use formal charges for that. Formal charges. To find the best structure. So when I was doing this, I was torn, should I do the formal charge video first or the resonance video first? Because you need formal charges to determine the best resonance structure. But there's not really a need for formal charges unless you have resonance structures, right? So I ended up going resonance first and then formal charge, but you really could interchange those. So let's do the next video on formal charges. We can bring this species back up again, and we'll go through and I'll show you why this one is has the most contribution to the overall structure. Not too tough, resonance.